because the harpoons didn't work because they didn't test them, basically. So they screwed up, big time. So where did it go? Well, that's a good question. People are looking for it, right? So the thought is that it flew away and bounced again and maybe again, off in this direction somewhere, but it's not in a place where it can easily be seen from the orbiting spacecraft. So we think that it fell into a crack. And we think that it fell into a crack or next to a cliff. Yeah, I can play this. This is the most pathetic piece of public relations propaganda ever made by any spacecraft anywhere. The touchdown sound. A, you won't be able to hear it because there's no sound system, I guess. But B, if you could hear it, it would be so stupid, you wouldn't want to hear it. It sounds like that. That's it. So they have microphones attached to the spacecraft. But they claimed to learn something from the microphone. They claimed that the impact was not instantaneous, at least the claim that I read, not instantaneous, that they penetrated a soft layer and hit something harder. Who knows? Anyway, this is a failed attempt at propaganda by the Germans. Here's the picture from the surface. So this is really a strange picture. But this is why they think it fell down a crack or is nestled up against a rock. It's because instead of seeing a nice picture of the horizon with jets going up, you look at this stuff. It's ice or rock or dirt or something. Here's just that picture shown by itself. Here's one leg of the spacecraft. And it's literally what you see if you go up to a cliff face on the Earth and put your face very close to it. It's full of fractures, it's covered in little boulders and bits of dirt. And it's not what they wanted. But the spacecraft did work. So the lander spacecraft did take measurements, and it did send many of them back to the mothership, which has then transmitted them back to the Earth. So overall, this has been a fantastic success, although not every aspect of that has worked. And here's a mosaic just showing some of the many, many nice pictures of this comet with its very, very peculiar and not well understood shape. So it is coming closer to the sun, and it's beginning to sublimate. This direct transfer from solid phase to gaseous phase, and that's happening apparently in the bridge material between the two ends. So these are jets of gas in which there's dust entrained and flowing out at high speed, and it's coming from that smooth region between the two major components. And there it is again in a more enhanced picture. You can see these very, very fine, high-velocity gas jets coming out of this nucleus. And there's just a nice picture of the whole thing. Okay, so I'm just about out of time. I guess the message of this talk is that we've understood a lot about the solar system in the last 20 years by thinking about and looking at comets. We understand the Kuiper Belt, which we didn't previously know to exist, much better than we ever could have imagined. It has important ramifications for understanding the dynamics of the solar system. We understand the Oort cloud a little better as well, because we do have more Oort cloud comets than we had 50 years ago, although its detailed structure and origin is still pretty mysterious. But we're starting to get very, very, very close-up geology-type pictures of comets, and in particular this one, 67P, is proving to be very, very spectacular and very, very mysterious. So I gave a similar talk yesterday at Central, and one of the questions was, so, okay, those are nice pictures, but what have we learned about comets? And it's hard to answer that question at the moment. Yeah, I think it's too early to say what we've learned based on these pictures. Anyway, I'll stop, and if you have questions, please ask me.
All right, thanks, Dave. So something I forgot to mention when I was talking about the things that Dave is interested in is he also is teaching an oceanography class at UCLA for the second time, I think, next semester. So if you have any questions about Rosetta, comets, or oceanography, please speak up.
If the lander works properly, could you tell us whether there's organic compounds on the comet?
Yeah, there's already some. Okay, so the deal is the Germans are very secret. The spacecraft teams in general, but the Germans in particular, are very secretive about this mission for reasons which people outside the mission don't fully understand. So I'm sure they have lots and lots of good, cool, excellent results that they're not telling us about for a while. They want to publish them first. It's a little bit understandable. Except that in a mission like this, the natural thing would be to tell people what you found, I think. But still. So the organics have been detected, but I don't know which organics. So we have to wait for the paper in Science. Now tomorrow, there's at least one, and maybe several papers will appear in Science, the magazine Science, describing some of this stuff. So the spacecraft has, mass spectrometers to measure the composition of the gas. It has other instruments to study individual dust particles, to capture them and then study them morphologically and in terms of their composition. It has a lot of interesting instruments, and we'll hear about them soon. But at the moment, we don't have the data. Outside the mission, we don't have the data. Yeah. But organics, sure. But, so what? We know the comets are full of organics already. So we know from thousands of ground-based observations that there are many different carbon-containing compounds in comets, in complexity going all the way up to amino acids. So it really matters which ones did they see, because we know the comets are full of organics. That's probably why they're so black.
Other questions?
Let me just make a theory right away.
Theory. Excellent.
Normally I don't do that. I think you told the spin axis towards perpendicular to the connection line between these two body collisions. Is that an observation?
Yeah.
It's 4 hours, right?
Yeah, there's like two things spinning around the line perpendicular to their
I
center.
think this would make people compare this direction versus the angular direction. You have I think you have, let's see. I think you have less pressure around the axis. No, I think you have more pressure because in the plane. You have centrifugal force.
Mm-hmm.
There's a pressure differential between the two axes.
Yeah.
So I would expect the one with higher pressure, we should melt faster.
Melt. No melting, right? Because there's no pressure, there's no melting. Yeah.
Sublimation.
Yeah.
So I think the thermodynamics could tell you higher pressure. Like you take a piece of ice.
Yes.
Wrap a.
I know. It's called regulation.
And then tighten it.
Right.
It will gradually melt faster than the.
But the trouble is the hydrostatic pressure. That's what you mean, right? Caused by gravity, is like nothing in this body.
I'm just wondering how big is that compared to the
well, it's okay. The density is 400, but it's hard to multiply by 400. Say it's 1,000. The radius is 2 kilometers. Let's say it's 1. So it's 1,000 times 1,000 is 1,000,000. And then gravity is 10 to the minus 5, I think, meters per second squared. So it's 1,000,000 times 10 to the 5. So the pressure is 10 newtons per square meter. So it's 10 to the minus 4 atmospheres.
Maybe not.
It's not a lot.
Go for it.
But congratulations on making a theory. I think the pressure is just so small. Yeah, because it's a small body and it's dense. Incidentally, about the rotation, there's no reason to think that the rotation is constant. Yeah. So the mass that comes off from those jets exerts a torque on the nucleus, and so the spin probably changes. 12 hours now, could have been 24 hours in the past, could have been much faster in the past, could have even been a bigger body that rotationally burst in the past. And the rotation axis can precess as well under the action of the torques from the mass loss. And there's also no reason to think that any of this is the primordial surface. So we know that sublimation can cause the body to shrink appreciably in a very short time, as we said in the beginning. And so it's quite possible that this thing was twice as big or 3 times as big when it entered the solar system and has lost a huge amount of material. It's entirely possible. People don't like to think that, but that's very likely. The trouble is, we don't know how long it's been close to the sun. We know its current orbit, but we can't integrate backwards because the orbits are chaotic. Yeah. Yeah.
Any other questions?
Yeah.
So in a movie of Gomes, you showed there's suddenly an explosion.
Yeah.
Can you explain what's the mechanism behind it again?
Okay, green means off, right? And red means on. So the idea there was that the orbits of the planets are being affected by scattering of planetesimals. And the strong effect occurs when, in this model, Jupiter and Saturn drifted into a mean motion resonance. Say the ratio of the orbit periods was 2 to 1 or something like that. When that happens, the gravitational force between the planets becomes periodic instead of random. And so the effects become very strong. So it's like shaking the solar system very, very strongly. So in that model, which is one of the more spectacular ones, they selectively picked that one out because it looks good. But all modelers will do that, of course. The vibrations caused by Jupiter and Saturn caused a planet that we would now call Neptune to be thrown into Kuiper Belt. And then Neptune has a large mass and a lot of gravity, and so it scattered all the other objects away. So it cleared the Kuiper Belt at that time, and basically destroyed the pre-existing Kuiper Belt. That's what they claim could have happened. And the issue is, how would we know if that actually is what happened? And so the answer to that question comes from what things are predicted by that model. And so people talk about that. And some people think that nothing is really predicted because the model has many parameters and it can fit the observations, but it doesn't predict anything. And other people try to argue that, yeah, there are some predictions, but they're not easy to understand. So at the moment, we don't know if that really happened, although many people believe that it did.
Maybe one more question?
So the Jupiter and Saturn actually flipped this position.
No, but Neptune and Uranus in this particular model flipped. They just like the idea of flipping a planet. There's nothing deeper than that. It's just kind of a cool thing.
Does that explain the Uranus being sitting on the side?
Uranus tipped over, probably because of an impact by maybe an Earth-sized thing. Yeah. But we don't know. Like many things in astronomy, we don't know.
Okay.
What was the board's idea about your discovery of hyperplan?
What? So that story? You heard that story? Okay. I'll do the story then. Okay, so there's history between Oort and Kuiper. So they're both great guys, but they were both Dutch. So Oort don't take that wrongly. So Oort was Dutch, and he stayed Dutch. He stayed in Holland. Kuiper left, probably something connected with World War II, I'm guessing, and came to the U.S. Oort was basically not interested much in the solar system. Most of what he did was concerning galactic structure. He was like the founder of modern astronomy in Holland. Really good guy. His graduate student was Kuiper, and they didn't really like each other. So, surprise, surprise. So Oort wrote this paper about the Oort cloud in 1950, and he made several assumptions and a couple of mistakes in the paper. One of the mistakes he made was that he thought the comets were ejected to the Oort cloud by Jupiter from the asteroid belt. So he calls them asteroids. So to him, because he's an astronomer, asteroids and comets are the same thing. He doesn't care. But the asteroids are not icy like the comets in general. So that's a mistake. And Kuiper knew that was a mistake. So Kuiper is sitting over there in Chicago somewhere. And he wrote a review chapter in which he argued that, well, maybe in the past there was a population of bodies in what we would now call the Kuiper belt, but that it must now be empty because he made his own mistake, which was thinking that Pluto was a massive planet that would clear the Kuiper belt. So he said the region where we see the Kuiper belt is empty. So it shouldn't really be called the Kuiper belt because he anti-predicted the Kuiper belt, but that's not part of this story. So the story that I think you're asking for concerns my colleague, Ken Chambers, from the University of Hawaii. So after we discovered the Kuiper belt in 1992, Ken Chambers, who was formerly a student in Leiden University in Holland, was on a trip back to Holland. And he saw Jan Oort in the hall. And he said, Jan, have you heard about this new discovery? It looks like the Kuiper belt is real. And yeah, according to him, Jan Oort immediately went white, shook his hand, had a bead of sweat come down his head, and said, no, rubbish, I don't believe it at all, and stomped away. And then later that night, he died. Yeah. So the claim was made for a little while, although I completely deny it, that I killed Jan Oort. I did not. But that's the story. So that's all true. So they hated each other. I don't know why they hated each other, but they did.
Probably a good place to end things. For those of you interested, Dave will be giving another talk tomorrow over in the astronomy building at 2:20, same time, about the part of his talk. Part of his talk will be on the part that he skipped today, so if you're curious, you can come to that. So with that, let's thank Dave again.